Black hole. A black hole is a region of space that has a gravitational force so strong that nothing, not even light, can escape it. They are formed when a massive star runs out of fuel and collapses under the force of its own gravity, creating a singularity, a point of infinite density and zero volume. Objects whose gravitational fields are too strong for light to escape were first considered in the 18th century by Jean Michel and Pierre-Simon Laplace. In 1916, Carl Schwarzschild found the first modern solution of general relativity that would characterize a black hole. David Finkelstein, in 1958, first published the interpretation of black hole as a region of space from which nothing can escape. Black holes were long considered a mathematical curiosity. It was not until the 1960s that theoretical work showed they were a generic prediction of general relativity. The discovery of neutron stars by Jocelyn Bell Burnell in 1967 sparked interest in gravitationally collapsed compact objects as a possible astrophysical reality. The first black hole known was Cygnus X1, identified by several researchers independently in 1971. Black holes of stellar mass form when massive stars collapse at the end of their life cycle. After a black hole has formed, it can grow by absorbing mass from its surroundings. Supermassive black holes of millions of solar masses, m, may form by absorbing other stars and merging with other black holes. There is consensus that supermassive black holes exist in the centers of most galaxies. History. The idea of a body so big that even light could not escape was briefly proposed by English astronomical pioneer and clergyman John Michel in a letter published in November 1784. Michel's simplistic calculations assumed such a body might have the same density as the Sun, and concluded that one would form when a star's diameter exceeds the Sun's by a factor of 500. And its surface escape velocity exceeds the usual speed of light. Michel referred to these bodies as dark stars. He correctly noted that such supermassive but non-radiating bodies might be detectable through their gravitational effects on nearby visible bodies. Scholars of the time were initially excited by the proposal that giant but invisible, dark stars, might be hiding in plain view, but enthusiasm dampened when the wave-like nature of light became apparent in the early 19th century. As if light were a wave rather than a particle, it was unclear what, if any, influence gravity would have on escaping light waves. Modern physics discredits Michel's notion of a light ray shooting directly from the surface of a supermassive star, being slowed down by the star's gravity, stopping, and then free-falling back to the star's surface. Physical properties. The simplest static black holes have mass but neither electric charge nor angular momentum. These black holes are often referred to as Schwarzschild black holes after Carl Schwarzschild, who discovered this solution in 1916. According to Birkhoff's theorem, it is the only vacuum solution that is spherically symmetric. This means there is no observable difference at a distance between the gravitational field of such a black hole and that of any other spherical object of the same mass. The popular notion of a black hole, sucking in everything in its surroundings, is therefore correct only near a black hole's horizon. Far away, the external gravitational field is identical to that of any other body of the same mass. Solutions describing more general black holes also exist. Non-rotating charged black holes are described by the Reissner-Nordstrom metric, while the Kerr metric describes a non-charged rotating black hole. The most general stationary black hole solution known is the Kerr-Newman metric, which describes a black hole with both charge and angular momentum. High-energy collisions. Simulated event in the CMS detector. A collision in which a micro-black hole may be created. Gravitational collapse is not the only process that could create black holes. In principle, black holes could be formed in high-energy collisions that achieve sufficient density. As of 2002, no such events have been detected, either directly or indirectly, as a deficiency of the mass balance in particle accelerator experiments. This suggests that there must be a lower limit for the mass of black holes. Theoretically, this boundary is expected to lie around the Planck mass, where quantum effects are expected to invalidate the predictions of general relativity. This would put the creation of black holes firmly out of reach of any high-energy process occurring on or near the Earth. Growth. Once a black hole has formed, it can continue to grow by absorbing additional matter. Any black hole will continually absorb gas and interstellar dust from its surroundings. This growth process is one possible way through which some supermassive black holes may have been formed, although the formation of supermassive black holes is still an open field of research. A similar process has been suggested for the formation of intermediate mass black holes found in globular clusters. 136. Black holes can also merge with other objects such as stars or even other black holes. This is thought to have been important, especially in the early growth of supermassive black holes, which could have formed from the aggregation of many smaller objects. The process has also been proposed as the origin of some intermediate mass black holes. Here are some interesting facts about black holes. Black holes are invisible. Since nothing can escape a black hole's gravitational pull, including light, they are invisible to the naked eye. However, their presence can be detected by observing their effects on nearby matter, such as stars and gas. Black holes come in different sizes. There are 3 types of black holes: stellar black holes, intermediate black holes, and supermassive black holes. Stellar black holes are the smallest and are formed by the collapse of a single star. Intermediate black holes are larger and may be formed by the merging of several smaller black holes. Supermassive black holes are the largest and are found at the centers of most galaxies, including our own Milky Way. Black holes can distort space and time. A black hole's immense gravitational force can warp space and time, causing them to bend and distort. This effect, known as gravitational lensing, can be observed by looking at how light is bent and distorted as it passes near a black hole. Black holes are not vacuum cleaners of the universe. Contrary to popular belief, black holes do not suck everything up like a vacuum cleaner. They have a specific range of gravitational influence, and objects that are outside of this range are not affected. Black holes can evaporate. According to Stephen Hawking's theory of black hole evaporation, black holes emit radiation, which causes them to lose mass over time. This process is incredibly slow for larger black holes but can be more rapid for smaller ones. Black holes have an event horizon. The event horizon is the point of no return around a black hole, beyond which nothing can escape. Anything that crosses this boundary is pulled into the black hole and is lost forever. Black holes may be key to understanding the universe. Black holes play an important role in the evolution and structure of the universe. They help to shape galaxies and other large-scale structures, and studying them can give us valuable insights into the nature of space and time. Black holes are one of the most mysterious and fascinating objects in the universe. Here are some of the biggest mysteries surrounding black holes. What happens at the singularity? The singularity at the center of a black hole is a point of infinite density and zero volume, where the laws of physics as we know them break down. It is unclear what happens to matter and energy that falls into the singularity, and how it behaves under the extreme conditions. What happens at the event horizon? The event horizon is the boundary around a black hole beyond which nothing can escape, including light. It is not clear what happens at the event horizon, and whether objects that fall into a black hole are instantly destroyed or if there is some form of delayed process. How do black holes form? While we know that black holes are formed by the collapse of massive stars, we still don't fully understand the exact mechanisms that drive the collapse. Or what factors determine whether a star will become a black hole or a less extreme object like a neutron star. Can we see inside a black hole? Since black holes do not emit light, it is impossible to see inside one directly. However, recent advances in technology have allowed scientists to observe the effects of black holes on nearby matter. And this has given us some clues about their internal structure. What is the role of black holes in the universe? Black holes play a key role in shaping the evolution and structure of galaxies, but we still don't fully understand their impact on the larger scale structure of the universe. Some theories suggest that black holes may be responsible for the mysterious dark matter that makes up a large portion of the universe's mass. Despite decades of research, black holes continue to be a subject of intense study and speculation. Ongoing observations and experiments will likely shed more light on these mysterious objects in the years to come.